Everything we've looked at so far with motion has been with respect to time, which makes sense. But that doesn't necessarily mean that we want the equations in terms of time. Because sometimes we don't care what the time is, we're just interested in the velocity at a particular position, a particular point. So how do we express velocity and acceleration in terms of the displacement rather than in terms of time? So if velocity is some function of x, we want it in terms of displacement, then there's this little relationship that the second derivative, or acceleration if you like, is equal to d dx over half v squared. Let's go and prove that. We know acceleration, the second derivative of displacement with respect to time, is the same as the first derivative of velocity with respect to time, so to v to t. Right? Now that idea is useful if I want to link velocity and time together. Let's take it a step further. I could use implicit differentiation, rates of change, call it what you will, and rewrite that as dv dx times dx to t. And dx to t is of course velocity. So I now have it written as dv dx times v. Now that's very useful when we want to link velocity and displacement together. But how do we get it back to this original thing I said? I now rewrite velocity and say, well, hang on, v is the same as saying, let's differentiate a half v squared with respect to v. And then the v's would cancel and you'd get d dx of a half v squared. So these two forms of acceleration become useful when we want to link velocity and displacement together. Okay, well let's look at some examples. Here's an expression for acceleration that's in terms of displacement rather than time. And we want to find its velocity equation then, and they've given us some initial conditions. We know that when it's at 1, its velocity is 2. Alright, d dx of a half v squared, that's 3 minus 2x. Therefore, if I integrate that with respect to x rather than with respect to t, I get this. Now they've given me some initial conditions, so I can work out the constant. In this case it happens to be 0. Velocity squared is 6x minus 2x squared, which means velocity is plus or minus. So this then brings up the question, well hang on a sec, how can a particle have two different velocities? And that's because we've taken time out of the equation. We're not saying it has the two velocities at the one time. We're saying, well, look, this particular particle is at this point at different times. At one time, it'll have a velocity of positive square root. At another time, it'll have a velocity of negative square root. So it is possible to have two velocities. But of course, that's doing it as an indefinite integral. I always use v to v dx and do it as a definite integral. I just find this a lot easier because now I can simply separate the variables. Again, here's my initial conditions. When x is 1, velocity is 2, I want to get a link between x and v. Now what happens is, when you integrate, there's where your half v squared appears all of a sudden. So you're still really using the formula, but it's just getting to it a different way, and I think a quicker way. Substituting in, playing around with it, we get the same equation, of course. Now this also brings up something interesting, because we know velocity squared has to be a positive number. Or another way of thinking about it, whatever's under the square root has to be a positive number. So I can get a bit of information about this particle. That means 6x minus 2x squared is always greater than or equal to 0. And if I was to solve that, I get that x is in between 0 and 3. So this particle leads a very boring life. It just travels between 0 and 3, and that's all it does. It just exists between those 2 points. Let's try this one then. Particle's acceleration is given by 3x squared. Initially, well, okay, we've been given initial conditions. Let's find the displacement time equation from this. Well, acceleration, I'll go straight to v dx, and I'll separate out my variables, and we integrate, and eventually, here we go, v squared is 2x cubed, so v is plus or minus root 2x cubed. Now we now want to get displacement in terms of time, and we know velocity is dx to t. But you'll notice I didn't write plus or minus, I just wrote minus. I have to make a choice as to which one I'm going to pick. Why did I choose the minus? Well, the initial conditions needs to satisfy my problem. And the initial condition was it was traveling in the negative direction. So when I substitute in the value, I need to get a negative velocity. So it's the negative velocity I want to use for this problem. Okay, put it in index form, separate out my variables, substitute in, or integrate first of course, substitute in, and we get this rather strange expression. But of course this is an expression for time. With respect to x, we want it the other way around. We're going to make x the subject, so we'll keep going. T plus root 2 equals root 2 over x, and eventually there it is. X equals 2 over t plus root 2 all squared. We have our equation. Particle moving along the x-axis. We love moving along the x-axis. Starting from a position 2 meters to the right. So just to help us out, they've clarified what that means, that x equals 2 when t equals 0. Initial velocity 5 meters per second, and they've given us an acceleration equation. Show that the velocity is x squared plus 1. Well, v to v dx, separate out my variables, place the initial conditions in there, x equals 2, v equals 5, bit of integration. You'll notice I didn't put a half v squared here, I just multiplied the other side by 2 straight away, because I know eventually I'm going to do that, so I'll just do that straight away. V squared is 2 lots of that. Substitute in, bring everything over, and that's a perfect square on the right hand side. So v equals x squared plus 1. Oh, hang on a sec. I need to explain why I didn't say plus or minus. They've asked me to show that. If I'd just written that down without an explanation, I probably wouldn't have got full marks. Because they've said, well, hang on, why did you discount the possibility that v is negative vx squared plus 1? But our initial conditions had it that way, so that's why we chose the positive. Hence, find an expression for x in terms of t. So very similar to the last example we looked at. Okay, I'll now make it dx to t. Separate out the variables. Ooh, an inverse tan function. Now we want to make x the subject. And I guess mere mortals would leave the answer like that, but we can do better than that. Tan plus tan on 1 minus tan tan, and we get a nice lovely expression there. X equals tan t plus 2 on 1 minus 2 tan t. So 6a.